Assalamu alaikum warahmatullahi wabarakatuh. Bismillahir Rahmanir Rahim. Inshallah, we'll continue talking about transformers. We gave some motivation and some introduction on the process that we do within the transformer or within the self-attention sublayer. Inshallah, we'll continue talking about self-attention today, inshallah. Just a recap of what we have gone through so that you can remember what we covered. We talked about self-attention. And self-attention is a process that takes n embedding vectors for the input sequence and produces same structure as an output sequence. Okay, so n embedding vectors also. Each vector is representing one token or one word, either in the input or output. The difference between the input and the output is that we should have a better representation for the output than what we started with. Okay, so this is the process of the self-attention. Last time we mentioned that it has two steps. First, we compute what we call value vectors, and then we compute the output vectors. Okay. And to compute the output vectors, we need what we call the self-attention weights. And this is where we stopped, I think, last time, where we were talking about how, or the first step in computing the self-attention weights. Yes. It's a sublayer. It's a sublayer in the transformer. Okay, but it is the main and the core idea in the transformer. So we need to pay a lot of attention to it. So the two steps that we mentioned last time, we compute the values first, given the input vectors, and this is done by a linear transformation with the weight matrix and biases without any activation function. And we mentioned that this is shared. The matrix and the weight matrix and the biases are shared across all the words. And then the output vectors will be a weighted sum of these values. Okay, so we compute the values and then we take a weighted sum of these values as the output, and the weighted sum is computed by the self-attention weights. Okay, so A here is the self-attention weights. And we mentioned that the self-attention weights are scalars, so are just numbers. We also mentioned that they are positive and they sum to 1 for each input vector. And I think we saw that last time. This is representing the weighted sum from the values to the outputs. So we first compute the values from the input vectors, and we mentioned that these are the weights. Okay, the weights that convert from inputs to values. And as you see here, usually, or what we covered so far in the course, that we have fully connected layers, right? So the connections between the nodes from nodes in one layer and the nodes in the next layer are complete, are full. Okay, that's what we saw before, but that's not always the case, of course. Here, the connections are not fully full, so we have connections between the embedding vector of x1 and the value vector of x1 separate from x2, the input vector of x2 and the value vector of x2, and so on. And these weights, we mentioned also that these weights are the same. Yeah, and it's not only that we have connections only within the same word, but these connections, which are the weights, are actually shared. So they are the same across the different words. And then the 0.1, 0.3, 0.6 here are the self-attention weights. Okay, and this is how we compute the output values by a linear combination or a weighted sum of the value vectors. Okay, so we mentioned all of that last time, and this is another example for the second word, and that's for the third word. And we also saw these representations that show that this is not fully connected. So this is the matrix that represents the transformation from the inputs to the values, and this is the matrix that represent the transformation from values to outputs. And if the network is fully connected, you would see that all elements here are colored. Okay, but because they are not connected, they are not fully connected, there are many missing connections, these cells are empty, which means that the weights are zeros in this matrix. We also saw this last time, and I think we stopped exactly here when we started to talk about how to compute the self-attention weights. Okay, any question on that? That's just a brief summary of what we covered last time. Okay, now how we can compute the self-attention weights. To compute the self-attention weights, we need first to compute two other sets of vectors called queries and keys. So far we created from inputs, we created value vectors, right? Values. We will also create or generate queries and keys vectors. Okay, and it will be in the same way we did the values, except that the weights will be different. So there are weights for queries and there are different weights for the keys. But again, they are shared. So the weight matrix for the queries are shared among all words, and the weight matrix for keys are shared among all words. Exactly like what we saw in the values, except that these are three different computations. Okay, so that means that from the input vectors, we will create three vectors, and each input vector will produce three vectors: value vector, query vector, and key vector. Okay, with me so far? Okay, and these are all with different matrices, but they are shared among the different words. Okay. Yes. So this is okay. So this is omega q. This is a matrix of weights. It's shared among all the input vectors here to compute the queries. So same matrix will be used to create the queries vectors. Okay. Same matrix will be used to create the keys vectors. Okay. Fine. Now let's assume that we have now the queries and keys. And in few minutes we will talk about the meaning of this, the intuition behind even the naming. Okay, but let's assume that now we generated the values, we generated the keys, and we generated the queries. Okay, now to compute the self-attention weights, we will compute what we call the dot product between each query vector and all the keys vectors. First of all, what do we mean by a dot product? It's multiplying two vectors, right? Okay, so it's a multiplication between two vectors. Each element is multiplied by the corresponding element, and then we sum them. Okay, this is what we call a dot product. So the dot product is just a scalar, right? It's just a number. Given two vectors, the dot product of them is just one number. Okay, so for example, we'll take the query vector of x3, which is this. We compute the dot product between this query vector and the key of the first word, which is k1. Okay, so q3 here with k1, and that will be on that number. Okay. No, every query vector with every key vector. Okay, so for example, this row, the first row, okay, it has three numbers. Each number is the dot product between the first query vector q1 with every key for the entire words, for the entire sentence or text. Okay, so this is the dot product of q1 and k1, q1 and k2, q1 and k3, and so on. Okay, now what is the size? If this is a matrix, what's the size of that matrix? Now it's 3 by 3. Okay, but in general, if I have n words, n by n, right? N by n, because every word we will have a value vector, we'll have a key vector, we'll have a query vector. Okay, every query will be dot product with the keys. Okay, so that means n square. Okay, n by n. Okay, and that makes sense, right? Because we want to get attention between every word and the other, right? Okay, so we will have a weight at the end. These are still not the self-attention weights, by the way. It's just an intermediate values. We will see in a second how we will compute the attention weights from them. But the number of values here represent what we want to get at the end. We want to get attention between every word and every other word, even itself, in the text that we are processing. Okay, with me so far? Okay, so this first row represents the similarity between x1 and all words. Now, when we talked about attention, what do we mean by the attention? What's the goal of computing the attention between two words or between one word and all the words? The relationship, right? To see how this word is related to the other word, right? One way of doing that is to compute the similarity between these words, represented by their vectors. Okay, so we can say that the first row here is the similarity between x1, the first word, and all words. Similarly, the second row is the similarity values between x1, x2, and all words, and so on. Okay, type. You notice that we are used the word similarity, right? Why is dot product considered a similarity? Actually, if you remember from linear algebra, the dot product is equal to the length of the two vectors multiplied times the cosine of the angle between them. So if the two vectors are close to each other, which means that the angle between them is very small, then the cosine will be close to 1 and the dot product will be high. So if they are close to each other, that means that they are very similar, right, in values, right? So in that case, the dot product would be really a large number. Okay, if the angle is 90 degrees, they are orthogonal. That means that they are they are independent. So the dot product in this case would be 0. Okay, because the cosine is 0. If they are reversed, like in this case, then the cosine will be close to -1, negative. So the dot product will be negative. Okay, so we can think of the dot product as a measure of similarity between the vectors. If they are close to each other, then we will have a positive high number. If they are reversed, then we have a negative number. And if they are independent, then we have almost 0 similarity. Okay, almost 0 dot product. So the dot product can be seen as a similarity. Okay, but question? Okay. Very good question. They are also not similar. In our context, in linear algebra, they are in opposite directions. But I cannot easily see it in words. What's the meaning of it to be completely? Oh no. Opposites. You mean opposite in meaning? I don't think so. If they are opposite in meaning, then their vectors should be opposite. Because if they are opposite in meaning, there is some relationship between them, right? But I don't think it's negative. In linear algebra, we can see that negative values, but in text, I don't see it easily to think of two words that have reverse direction in vectors. Okay, but overall, when the similarity is getting higher, positive, then if the dot product is getting higher, then that means that they are more similar. Okay. Now, you remember that we said that earlier, that the self-attention weights are all positive and sum to 1. the dot products, as we compute them, they are not like that. They could be negative, okay, and they could be high values, right, large values. So there's no way we expect them to be positive all and sum to 1. But we can force them to be positive and sum to 1 by a way that we already saw in the course before. Any ideas? By the softmax, okay, by the softmax function. So what we will do actually is to take each row here, which represent the similarity between one word and all the words, and apply the softmax function to it, which means that we will convert all values to positive values because we will raise them to the exponential, and then we normalize them all by the sum, which means that they will all sum to 1. Okay, so we'll compute the dot products and then we apply the softmax on every row, independently, of course, each row separately. And if we do that, then the three values here will be positive and sum to 1. And that's why, if you remember in the example before, it was 0.6, 0.3, 0.1, right? Positive and sum to 1, because we will do softmax to force them anyway to be like that. That's not guaranteed from the dot products, but now if we apply the softmax function, then we would get them all to be positive and sum to 1. Okay, now we can call them the self-attention weights. Now these are the self-attention weights that we will use to compute the output vectors. Okay, so you can think of this as like the 0.6, 0.3, 0.1. Now we can use these weights combined with, applying them to the value vectors to get the final output vectors. So these are the attention weights for x1, and this is the whole matrix that we saw before, but it's like reflecting these individual self-attention weights in the entire matrix. Okay, you can see that this weight is repeated here, and this weight is repeated here, and this weight is repeated here. If you want to think of it as a transformation matrix between the values to the output vectors. Okay, any questions on that? Yes. Yes, sure. Here? Mm-hmm. Maybe, maybe. Not 100% guaranteed, but yeah, you can think of it that way, maybe. Okay? But you can also think that whenever it is large number, including positive, of course, then there is a high relationship or high similarity, and otherwise it would be a low similarity. Okay, and when it gets in an absolute sense larger in the negative direction, it's less similar. Okay. Okay. And of course, if we look at one value of this matrix, then this is how much, this, for example, which is this value, it's representing how much the third word attends to the first word. What does that mean? And if this number is 0.8 or 0.9, what does that mean? Yeah, that means that this word should attend much to that word, which means that this word should influence that word. Okay, it's very related to that word. Okay, and that's in a matrix form. We have now a matrix for the queries, okay, and biases, weight matrix and biases. Another weight matrix and biases for the keys. Okay, we generate the queries and keys, and then we compute the similarity between every query and all the keys. Okay, and this is the softmax function. So eventually we will have one number for every pair of words. Okay, and remember that we compute the dot products between the queries and the keys. Okay, and the similarity here is done by computing the dot products. And just to complete the picture, after we compute the self-attention weights, what do? Yeah, we do the weighted sum. Okay, so this is like the 0.6, 0.3, 0.1. We computed them already. Now we multiply 0.1 by that vector, 0.3 by that vector, 0.6 by that vector, and sum them to get the output vector for x1. Okay, same for x2, but of course with different weights. Okay, and same for x3 with different weights. Okay, now just a quick question: where can we find these three numbers in the matrix that we saw in the previous slide here? Where in that matrix? So we have this matrix, right? The three numbers here, 0.1, 0.2, 0.7. Where are these in this matrix? The three numbers where what? Where the self-attention weights between, not each word. Between, let's get back here. Okay. These three numbers are the attention weights between x3 and all words, right? Where is that in the matrix? The last row. Okay, is that clear? Okay, right. Now what's the intuition behind that? Okay, I hope that you understand now how the computations are done, right? Why do we call them queries and keys and values? What's that? What's the meaning of that? Okay, I will try to explain that by comparing it with a real scenario. Okay, what's the real scenario? Imagine that you are in a library. I don't know if you went to a library ever nowadays, but let's assume that we went to a library and we are searching for a specific topic in the library. I'm searching for books that are relevant to that topic. Okay, so I will start with having a topic in my mind, right? And now I have the books in the library. What should I do? Okay, so let's say that there's no such sections. Okay, so I have to look at every book, right? I have to look at every book. Should I read the entire book? No. What should I do? Read the title, maybe some part of the introduction, maybe the keywords, right? So I will do that next. So I will check the titles and the keywords of the books. Okay, then, huh? It's not just one book. I'm looking for a topic, right? So it can be part of that book. It can be one chapter of that book. It can be multiple chapters in that book. It can be one page in that book, right? And then I will gather or retrieve these books, okay, and read them, right? So that's the third step, is to retrieve the books that match the topic that you have, right? So you understand this process, right? Okay. How does that compare to what we did? Where are the queries? Where are the keys? Where are the values? Which is, if when we talk about that, the topic is the query, right? The query that I'm looking for. Okay, so that's why we call it the query. Query is the thing that I'm looking for, right? When you type something on Google search box, this is the query, right? When you want to retrieve something from a database, what you write is a query, right? So the topic that I have in mind is the query. Okay, now I compare that query with what? With the keys. Okay, with the keys, not with other queries, right? Okay, with the keys, which represent the main information in the items that I am searching in. Okay, so these are the keys, right? Now, after I match these keys, I found مثلا that key 12 and key 27 are the most similar. What should I do? Should I just read the title again and that's it, or get the book itself of the two books themselves, right? So the books here are the values. Okay, are the values. So we compare the query with all the keys. We compare the topic with all the books. Okay? With not all the books entirely, but with the main information of the books, which are in this case the titles and the keywords. Once we find that there is a match, then we retrieve the book itself, which are the values. Okay, but we also retrieve it with maybe like what I said. It's a page from here, chapter from here, multiple chapters. What are these in our scenario, in the transformer? What is this? When I say this is just one page from here, couple chapters from here, maybe half the book from here. These are the attention weights, right? These are the attention weights. Okay, very something that's very small from that book, much bigger from that, a lot from that, and so on. Okay, and then I combine them. I retrieve the book itself, and then I read it. Okay, so when we say we check the titles and the keywords, we match the query with the keys. Okay, and checking here is like the dot products that we do. Okay, and then when we say the books that match, that means that we are talking about the attention weights here. And when we retrieve the book, it's like we sum the weight. We have the weighted sum of the things that match. Okay, did you get it now? And that's why actually they are called queries and keys and values. Okay, the naming here is adopted from my own special research area, which is information retrieval. They use queries and keys to search for the things that we yes. No, the values are okay. Let me show you the next slide then to give you a textual meaning of each. Okay, the queries are the things that we are searching for. Okay, so the query of a token, this is what the token is seeking, what information it needs. Okay, the keys are the information the token holds, which means how relevant it is to the other queries. So that's the main information that, as a token, I provide. Okay, but the values is the entire content, the actual content of the word, the whole representation of the word that I will actually use. Okay, that's why at the end we have a weighted sum of the values. Okay, it's not a weighted sum of the keys. Okay, so of course this is an intuition. That's how the design was chosen. Okay, based on these intuitions that we have queries, and these queries like searching or matching with the keys. And once we match with the key, we find back we get the actual value of that key. Okay, remember in databases we have index, right? The index is just by part of something that identifies the records, right? Did you study databases or not? So when we index, we have like if I index students, I index students by IDs. Okay, so I search in the IDs, but when I use the information, I get the entire record now, right? I don't use just the ID, right, for the student. I want the address and GPA and all the information about the students. Okay, so I use the value of the student. Okay, not just the key of the student. No, the keys. The yes, it's generated from the input. So I start by the input vector. I generated three things. I generate the queries, which represent what this token is seeking. Entirely, exactly. Yes, keys, queries, and values. I use the keys and queries to compute the dot products, which are the self-attention weights. Okay, and then after I compute the self-attention weights, I apply them to the values to get what I want. Yes. The input just is there to generate from it the three things. No, no. Okay, type. Let me show you first this attention, and then I will go through an example. Okay. So this is an example of the self-attention. Remember this sentence we started with last time? The animal didn't cross the street because it was too tired. Okay. Now, this is just an example to show you how attention actually is useful. The word it here, if you look at the attention when after, of course, training that model, it attends. So these connections first are the self-attention weights. If they are stronger, that means that the weight is higher. Okay, so that means that it attends much more to the animal than the other words. Okay? And that's exactly what we want. We want things like that. We want relationships between the words that um, will represent the meaning of the entire text snippet. Okay, so this is an example of self-attention. And now, just to give you the whole picture, we started with the goal of designing a model to encode and process text, and we eventually we got a model that has parameters, okay, that don't increase with the input length, and also show or generate connections between the words, and the strength of these connections depend on the words themselves. So we have connections between, or attention weights between every word and all the words in the text. And what are the parameters of that model? When we say parameters, these are the learned parameters, right? The parameters that we will learn. That when we train the model, this is what we will get. Okay. What are the parameters that we have here? The weights and biases, right? Just one weight matrix and one bias vector. 3. 4 values, 4 queries, 4 keys. Okay, and these are the parameters. Okay. Now, to see it more in a matrix form, we start with the input. Okay, we saw that before, right? It's every column here is what? Is an embedding vector for one word. Okay, we generate, as you see now in parallel, queries, keys, and values from that matrix using the weights and biases for each side. Okay, so in parallel we can compute all of these. Then we use the queries and keys to get the self-attention weights. Okay, and then use the self-attention weights, apply it to the values to get the output values, the output vectors. Okay, it looks like a complicated process, but I hope that now you understand the steps and you understand the intuition behind them. Yes. Yes, you see this structure is exactly like this, right? So we started with a vector for each word of length d. We will end up with a vector for each word with length d, but of course it's different after getting through the attention. Yeah. Each output vector. Yes, it's a column here, by the way, not a. Oh, yeah. Exactly. That's why it should be better now. Okay, better than what we started with. Okay. Okay. And this is in equations. Okay. So again, values, queries, keys, applying the weight matrix and bias. And notice here there is no what? No activation function. It's just linear. Okay, it's linear layer, and then we apply the softmax between the keys and queries and multiply by the values. This slide shows you that we don't need to do it one by one. Yani. We don't compute the dot products one by one. It's just matrix multiplication again. Okay, all of these are matrix multiplications. Okay, eventually we'll get a matrix that has all the output vectors for all the words. Yes, sure. This one. Yeah. Yes, Yes, but represented, each word is represented by a vector, of course. Yeah. The what? Ah, okay. Where is it here? It's one column in this matrix. It's if it's the third column here, then its output vector is the third column here. After computing the okay, we do a weighted sum, right? When we do a weighted sum, it would be a vector again, but it's a weighted vector of the other vectors, of the values vectors. Hmm. Okay. I think I got your question. If we get back to this, you're saying where are these? Okay, where are these? That's the question to you now. Okay, let's get back here now. Where is it? Where are these connections in this slide? Where is it? Is it in that slide? Yeah, can you point to where in that slide are these connections? V. This one. طيب يعني let me be more explicit. Let's assume that this connection to the animal is zero point 0.7 مثلا. Okay, where is 0.7 here? Where in that matrix? Do we see it in that matrix? Do we see it in that matrix? Where? Let's assume that it is the third word, and sorry. No. Okay, it is the fourth word, and animal is the second word. Okay, tell me. Fourth column, second. No, Fourth row, second column. So it's here exactly. Okay, so that should be now 0.7, and that's what is um, pictured in the figure. That's illustrated in the figure. Okay. Oh, of course. Here in that figure we are showing the attention weights. Okay, so these are the attention weights. Of course, after computing the attention weights, what will happen? First, apply by these weights to the vectors, to the value vectors of those words, and compute by the output vector of that, which is where بقى هنا? Which will be the fourth, because we said that it's the fourth word, right? So it will be the fourth column here. That's the output vector of it, of the word it. No, it will be as is, but that's the weighted sum of the other vectors. No, there is no here in that output vector. There is no meaning of, there is no indication of high values and low values. This is just a representation of numbers. Okay, good question. So the question is, yani, what will we do with that? صح? Okay, so we computed all of that. وبعدين يعني what should we do? Any answer? So we computed the attention weights, right? And from the attention weights, we computed the output vectors. Okay, then what? Yes? Yes, we are not done yet. This is a sub layer within one transformer layer, which is one layer within the transformer. Okay, so we are not done yet. Okay, so stay tuned. But at least you understand now that that representation should be better than what we started with, because it considers the attention to other words. So far we are focusing on starting with some representation and getting at the end a representation that is better. Okay. Now let me show you an example. Okay, just to make sure that you really understand what's going on. Let's assume that we started with a sentence that has two words only, and don't worry about the meaning. Okay, two words, x1 and x2. Okay, So we started with two input vectors, right? These are the two input vectors. And from these two input vectors, we generate the queries vectors, right? Using this matrix. And we generate the keys vectors using this matrix. And we generate the values vectors using this matrix. Okay? Now I want to compute the attention weights of x1. What should I do? What do you mean it? Tell me the name of the vector. All the vectors have names here. Q1. We get the dot product between Q1 and K1 and Q1 and K2. These will be two numbers, right? The dot products. Then sum them. Softmax. Softmax. Apply softmax to get the attention weights. Type after we get the attention weights. Apply to V1 and V2. Okay, and that are the steps now. So step number 2, compute the dot products Q1 K1, Q1 K2. Okay, then we forget about this. We didn't talk about it yet. Okay, so just ignore this, and then we apply the softmax on these two values. Okay, now before we apply the softmax, when I tell you that the values are 112 and 96, do we get any meaning of that? The relation between Q1, not Q1, the relation between X1 and X2 and X1 itself is higher than the relation between X1 and X2. Okay, so we expect that the attention weight for X1 will be higher than X2, of course. Huh? Not always. We saw it in it, right? It is attending to another word than itself. Okay, so it can happen. Okay, so from that we compute the softmax values. Now softmax values is 0.88 and 0.12. What do we do next? We take this 0.88 multiplied by V1 and 0.12 multiplied by V2 and sum them to get the output vector for X1. So that's what we do here. So this is softmax times the value, and this is softmax times the value. You can see that this is stronger than this, right? Because that was a higher number. And sum these two to get the output vector for the first word. If I want to get it for the second word, same thing, right? But now I compute dot products between Q2 and K1 and K2 and so on. Okay? Questions before I ask, because I have questions. Ready for the questions? Okay. All right. An output vector in the self-attention sublayer is a weighted sum of values vectors, keys vectors, queries vectors, all of them. Yes. What do you think? The output vector is a weighted sum of values only. It's a weighted sum of values only, right? What did we do? What did we do here? It's the weight. These are the weights. So the output is a weighted sum of these two vectors, right? It's straightforward, right? It's weighted sum of what? Of the value vectors, right? Right. Next one. Computing the output vectors in the self-attention sublayer is dependent on, what do you think? Is it all of them or values vectors? All of them. Why is it all of them? Yes. So it's a weighted sum of the values, but this weighted sum, this the weights come from the keys and queries. Okay. So it depends on all of them. Okay. And I think we will stop here. Do you have any questions? Okay. See you inshallah next time. Assalamu alaikum wa rahmatullahi wa barakatuh.